My dear students, we have completed chapter number 1. I have given you some questions of the exercise of chapter number 1 as a homework. So please do all those numerical questions and submit the homework to me as soon as possible. We start chapter number 2, and the first topic of chapter number 2 is the ray theory of light. So optical energy follows narrow paths. These narrow paths are known as rays. The maximum speed of the light ray occurs in free space, that is vacuum, and the maximum possible speed of the light ray is 3 into 10 raised to power 8 meter per second. This is the maximum possible speed of the light ray which takes place in vacuum, which takes place in free space. In any other medium, the speed of the light ray is less than 3 into 10 raised to power 8 meter per second. And we know the mathematical equation which is used to find out the speed of the light ray in any other medium. We can calculate the speed of the light ray in any other medium with the help of V is equal to C by N, where N is the refractive index of the medium. Rays follow straight paths unless deflected by a change in the medium. If a light ray travels in the same medium, its direction does not change. The direction of the light ray will be changed by a change in the medium. If there is a change in the medium, the ray will be deflected and thus its direction will change. When a ray travels from one medium to another medium, its direction changes. So the direction of the ray changes when it travels from one medium to another medium. And whenever a light ray travels from one medium to another medium, a fraction of the incident energy is reflected back to the same medium. And this ray, which is reflected back to the same medium, is known as reflected ray. This situation is shown in this figure. On the left hand side, we have got medium number 1. The refractive index of medium number 1 is N1. On the right hand side, we have got medium number 2. On the right hand side of the interface, we have got medium number 2. And the refractive index of medium number 2 is N2. The plane boundary between medium number 1 and medium number 2 is known as interface. So on the left hand side of the interface is medium number 1, and on the right hand side of interface is medium number 2. You guys can see normal to the interface in this diagram as well. So if we look at the incident ray makes an angle of theta I with respect to this normal. and a fraction of the energy of this incident ray is reflected back to the same medium, that is medium number 1, which is known as reflected ray, and the angle of the reflected ray with respect to the normal is represented by theta r. The angle of the incidence is always equal to the angle of reflection. Theta I, which is the angle of incidence, is always equal to theta r, which is the angle of reflection. So theta I, the angle of incidence, will always be equal to the angle of reflection. So whenever the light ray travels from one medium to another medium, a fraction of the incident energy is reflected back to the same medium, and the remaining energy of the incident ray is transmitted to the second medium. The energy which is transmitted to the second medium and which travels in the second medium is known as transmitted ray, and you guys can see the transmitted ray in this diagram. You see, the direction of the transmitted ray changes. The direction of the transmitted ray in medium number 2 is different from the direction of the incident ray, which is in medium number 1. The incident ray and the transmitted ray are not in the same direction. The angle of the transmitted ray with respect to the normal is represented by theta t. So theta t is the angle of transmission. The incident ray and the transmitted ray obey Snell's law of reflection. And the Snell's law of reflection is shown in equation number 2. In equation number 2, n1 into sine of theta I is always equal to n2 into sine of theta t. We already know that n1 is the refractive index of medium number 1. Theta I is the angle of incidence. N2 in equation number 2 is the refractive index of medium number 2. Theta t is the angle of transmission of the transmitted ray. So the incident ray and the transmitted ray obey Snell's law of reflection, and this Snell's law of reflection is shown in equation number 2. It is given in equation number 2. If n2 is greater than n1, if the refractive index of medium number 2 is greater than medium number 1, then according to Snell's law, the angle of transmission will be less than the angle of incidence. And if the angle of transmission is less than the angle of incidence, definitely the transmitted ray bends towards the normal, as shown in this figure. You see, in this figure, the incident ray, the light ray, travels from medium number 1 to medium number 2. Medium number 1 is air, and the refractive index of the air is 1. Medium number 2 is glass, and the refractive index of the glass is 1.5. So in this diagram, the incident ray travels from a medium of low refractive index to a medium of high refractive index. Its direction changes and the transmitted ray bends towards the normal. We consider another case. If n2 is less than n1, then according to Snell's law, the angle of transmission will be greater than the angle of incidence. And if the angle of transmission is greater than the angle of incidence, then the transmitted ray bends away from the normal. So let us consider this condition in this figure. In this figure, medium number 1 is glass. And we have already discussed the refractive index of medium number 1, that is 1.5. Medium number 2 is air, and we have already discussed the refractive index of the air, that is 1. So in this diagram, the incident ray travels from a medium of high refractive index to a medium of low refractive index. So whenever a light ray travels from a medium of high refractive index to a medium of low refractive index, the ray bends away from the normal. Let us discuss this principle of light rays from fiber optic communication point of view. At the transmitting end, we feed the ray from the air to optical fiber. A fraction of the incident ray, a fraction of the incident energy reflects back to the air. So the reflection of the energy of the light ray will take place from the transmitting end of the optical fiber. And we don't want this reflected ray at all, because due to this reflection phenomena, the energy will be lost. The loss will take place because of this reflection phenomena. We want the entire energy of the incident ray to move to the fiber. The loss which takes place due to the reflection phenomena is known as reflection loss. We need to eliminate this loss. If we cannot eliminate it, at least we need to minimize it. This situation is shown in this diagram. You see, we want to feed the incident ray from the air to the optical fiber. So the incident ray travels from a medium of low refractive index to a medium of high refractive index. And a fraction of the incident energy is reflected back. This reflected energy is represented by reflected ray. So we don't want to have this reflection ray over here because of the reflection loss. The reflection loss will take place in this particular case. As the light ray travels from air to the optical fiber, it bends towards the normal. We discussed this principle a while ago. We say that whenever the light ray travels from a medium of low refractive index to a medium of high refractive index, it bends towards the normal. So in this particular case, as the incident ray travels from the air to the optical fiber, it bends towards the normal. The situation, the scenario is shown in this particular figure. You see the transmitted ray in this particular figure bends towards the normal. Let us do example number 2.1. Example number 2.1 says a light ray proceeds from air into glass. In example number 2.1, a light ray travels from the air to the glass. The refractive index of the air is 1 and the refractive index of the glass is 1.5. There are two parts of example number 2.1. We need to find out the angle of transmission if the angle of incidence is 0. This is part 1. And we need to find out the angle of transmission if the angle of incidence is 15 degree. So let us do this example number 2.1. So in this numerical example, N1 is 1, N2 is 1.5. In the first part of the numerical question, the angle of incidence is 0 and we want to find out the angle of transmission. So we apply Snell's law. That is N1 sine of theta I is always equal to N2 into sine of theta t, and we rearrange this particular equation. If we rearrange this equation, the rearrangement gives you sine of theta t. And sine of theta t is equal to the right hand side. What is on the right hand side? We have N1 sine of theta I divided by N2. And we simplify the second last equation for the angle of incidence. So, not for the angle of incidence, for the angle of transmission. So we can calculate the angle of transmission with the help of the last equation of this slide. So let us put the values on the right hand side of this last equation. If we put the values on the right hand side of the last equation of the previous slide, the angle of transmission comes out to be 0. And this scenario is shown in the following figure. You see, on the left hand side of the interface, the medium is air and the refractive index of this medium is 1 and 1 is 1. On the right hand side of the interface, the medium is glass and the refractive index of the glass is 1.5. The incident ray is normal to the interface. Why? Because it makes an angle of 0 with respect to this normal. Similarly, the transmitted ray is parallel to the normal because it is perpendicular to the interface, and it is parallel to the normal because it makes an angle of 0 with respect to normal. So if the angle of incidence is 0, the angle of transmission will be 0, and the direction of the transmitted ray does not change in this particular case. The direction of the transmitted ray does not change in this particular case. Let us do the second part of this particular question. The angle of incidence in the second question is 15. We need to find out the angle of transmission. So we already know how to calculate the angle of transmission. We can calculate the angle of transmission with the help of sine inverse of N1 into sine of theta I by N2. We put the values in this equation and we get the angle of transmission, and the angle of transmission is 9.94. This scenario is shown in this figure. On the left hand side of the interface, the medium is air, the refractive index of the medium is 1, while on the right hand side of the interface, the medium is glass and the refractive index of the medium is 1.5. The incident ray make an angle of 15 degree with respect to normal. As this ray travels from a medium of high refractive index, from a medium of low refractive index to a medium of high refractive index, it bends towards the normal. So the angle of incidence is 15, while the angle of transmission is 9.94. Let us do the second example of the book. This example says the lost ray in example number 2.1 now travels from the glass back into air. Assume that the second boundary is parallel to the first one. The new incident angle is 9.94, as can be seen from the figure on the next slide. You see, this is figure number 2.5 in the book, but we will show you the figure on the next slide in a while. Find the direction of the transmitted ray. Okay, so we calculate the angle of transmission with the help of the same equation. We have already, you see, discussed this equation. We have already derived this equation in the previous slides. So N1 in this particular case is 1.5. Why? Because the light ray travels from the glass back to the air now. So medium number 1 is glass. And the refractive index of the glass is 1.5. The angle of incidence is 9.94. And N2 in this particular case is air. This is the refractive index of the air. So N2 is 1. So if we calculate the angle of transmission comes out to be 15. The scenario is shown in this figure. You guys can see interface number 1 and then interface number 2. Interface number 2 is parallel to interface number 1. So initially, the incident ray travels from the air to the glass. The incidence angle of the incident ray in the air is 15 degree, while the angle of transmission of the transmitted ray in the glass is 9.94. Now this ray, this transmitted ray from the glass travels back to the air. It travels to the air now. So in this particular case, medium number 1 will be the glass, the refractive index of which is 1.5, and medium number 2 is air, the refractive index of which is 1. So you see, as this ray travels from the glass to the air, the transmitted ray makes an angle of 15 with respect to normal. And you see, the overall direction of the ray does not change. The ray travels with an angle of 15 degree from the air to the glass, and then the same ray travels back to the air with the same angle of 15 degree. So the direction of the ray does not change. The overall direction of the ray does not change in this particular case. Thank you so much.